today I just have 5 decks, 5 or 6 probably, and there are a bunch of things in my notes. So the other day in our group there was a discussion that the Google announced about Willow. Then Microsoft is announced something around Mozorona. So what's happening at the hardware level? Are we really doing so many big breakthroughs back to back? So I thought of doing a field study, so that what are the basic technologies which are currently available for building quantum hardware, and how they are poised, what are their strengths, what are the challenges, and who are the companies who are leading it. So that was my curiosity. And it what helped me is there is a special issue of New Scientist. Somehow I got it through my BCL membership, and I was able to read that, and that article were quite detailed. I took some following readings as well, but the the information mostly is around recent announcements by different tech giants and the articles that I read from New Scientist. Unfortunately, that New Scientist articles are not free. So, and my subscription to BCL membership is limited to the tablet. So I'm unable to actually create a soft copy of those articles as well. Okay, so we'll start quantum hardware, tech, and players, and we'll complete it in not more than 15 minutes, and then Praneeth will talk about the quantum computing where security application stands here. He recently presented in another forum, and he will repeat that talk here as well. Okay, let's move on. So what is the expectation for quantum computing? So we all know, we have gone through this for 9 months now. So quantum computing should solve complicated stuff which cannot be solved in classical computers. That's the single statement requirement from quantum computing. Now, as we have all seen different angles during our course of study, what's needed for that? Number one, okay, Aman is. So Aman, we just started. This is the second deck. The first one is the title deck. So we are reviewing what is the expectation from quantum computing today. So so we just said quantum computing should solve complicated stuff.
Sure, Debansu. Thank
Okay.
you for letting me in.
Okay. So that's in the left side we have the expectation noted down from quantum computers, and what's needed to achieve that state is computers which should be large enough to run complicated calculations, and that's where classical computer will fail. Obviously, there are quantum advantages, and all. We'll not discuss those things today. And while doing this calculation, make fewer errors. This is the utmost requirement for all the quantum computers that we build, whatever technology is used and stuff. Okay, so let's go to the next slide. So what it means actually, uh, number one, qubit needs to be in its state longer. So we all know uh, qubits are basically state of a system. For example, in bits, it's a high voltage or low voltage. High voltage, if high voltage is represented at +1, and then low voltage is 0. So these are two states, and all binary mathematics are based on those two states of the system. Now, in qubits, we know that it's a mixed state, right? Ket 0, alpha ket 0 plus beta ket 1, and that's when we express this in base measurement coordinate system. There are other systems where these things will change, but then all we refer to is a state. Now, what is the first thing is this state should stay longer, so that we can encode things to the state. Basically, the information should be encoded to the state, and then later on we change the state to do some operations, like we run a Hadamard gate or run a CNOT gate or whatever be the case. Basically, circuit logic we apply on those states and then measure it. Okay. The second thing is demonstrate coherence. In physics, coherence means been being in synchronized state for long. So that's coherence. There are other mathematical meaning of it, but let's not get into it. Surya knows it. Most of you know it. Uh, Now, controlled operation can happen resulting in a calculation. So the state should be longer coherent so that controlled operation can happen, and it should result in end of a calculation. And when the state gets into decoherence, so the result in measurement happens, and it should be like it happens in a merger of a classical state from which we get the result of the calculation. We all know it, like wall quantum operation, wall circuit operation. Basically, it's a classical data, put it into quantum state, encoded into quantum state. We run bunch of operations to which reflects our algorithmic states, and then the when we observe it, the quantum state merges in a classical state and it gives the result. So what actually it means, that need of error correction and all those things, error free operation, it boils down to these 4 5 things. Now, how we can do the error correction? We know that coherence is very small. So microsecond, nanosecond is the timeline when wherein the state actually stays in a state of the circuit. Now so what we can do to achieve this error correction? Because we all know that whatever hardware is present today, all the hardware, quantum hardware, are noisy. And the moment we say okay, so these particles or this set of topology is reflecting to a state, the other moment it can flip. Now, what are the general approach to mitigate that? The major approach is basically use cluster qubits instead of physical qubits. So basically, we talk of logical qubits, which composes of multiple physical qubits, and then we cluster physical qubits, mark them as logical qubits. So, for example, if you think of 107 qubit quantum computer, you may actually expose 7 logical qubits, which are actually operational qubits on which you can run the operation. Okay, so encode state in multiple qubit. That's where the scalability factor comes in. So if you increase the number of physical qubits, obviously the cluster number of clusters will increase, number of logical qubits will increase, and it will give you more error prone hardware, I mean error immune hardware. And the other approach is called a bosonic approach. Recent Amazon announcement on some breakthrough around bosonic approach is basically when you encode a qubit, we are generally encoding it in a Fock state, right? Harty Fock state is where we do most of our quantum calculation. But bosonic approach says we just encode it in a Hilbert space, which is infinite dimensional. So you have redundancy of the encoding. You encode in multidimensional space. So if one dimension doesn't give you the correct state, then go to the another dimension and find the state. So if there are such encoding in 5 such dimensions, you at least get a result from one of those dimensions. So that's called bosonic approach. And I think the recent AWS announcement ignore and consider the fact that I work for Amazon. So whatever statement I make can be biased. So read it, read the articles when you analyze this. Okay, now so these are the two things. We have to make the qubit stable, so make the coherence time higher, and reduce the noise. So these are things to scale up quantum computing, so that our first requirement, which is do something significant which is not doable in a classical computer, can happen. So let's get to the technologies now. Now, the most formidable technology, which is which is in place for many years now, okay, is superconducting circuits. Okay, so superconducting circuits, I'm not getting into the physics of it. What we can do is later on, say for example, Today, I am talking about the overall thing. Say someday Surya takes up superconducting and does her research and present us a superconducting talk, or some other day the other tech, someone else picks up and talk about it. So that can be one approach in talking, going deeper. So today we'll make it superficial, not going deeper to the physics of it. So the strength of superconducting circuits is relatively mature technology as of now, with significant progress in scaling. So people are talking about roughly around 1,000 qubits available in different claims. We'll see. IBM is very confident. As I said, last Saturday, I was at ACM conference in Coimbatore, where the head of IBM Quantum in India, Venkat, was talking about. They are very confident. They are saying 2020-26 would be next big thing for IBM. Okay. So the fabrication techniques are somewhat compatible with the existing semiconductor manufacturing process. This is the primordial advantage. And gate operations are faster. So if you interface it, it cannot be electrical wires, some sort of other things. So it operates pretty fast. So that way, this is the tech which is most mature today. But wait a bit, because I will come to a different tech which they are saying people are seeing as more promising. What are the weaknesses? Huge noise, as we already started discussing. It's susceptible to noise and decoherence, requiring extensive error correction. I had actually a anti comment from Venkat. Actually, Venkat said, think of your laptop versus server platform. The servers usually have ECC RAMs, which is error correction code embedded into the RAM, but your laptop doesn't have a RAM, which is ECC. It doesn't have a error correction embedded. Doesn't your laptop work? Okay. So that opened up my eyes actually. So if at software level, if we are able to tackle the errors, then obviously there is a possibility that at hardware level error correction may not be that important if number of qubits are very large. So at software level itself, people can take care of that most probably. That's what he was hinting around. But obviously, it is a weakness. It requires extremely low temperatures, actually cryogenic temperatures, and connectivity limitations. You can't really put wires and all these things stuff. So what are the companies who are working on these superconducting circuits? IBM for sure, Google, Rigetti, Alice and Bob. Alice and Bob is a startup. I haven't really found out a lot of data about it, but others are well-known companies as of now, so you can find more details about it and where they're located and all those stuff. Okay, the second tech is Traptown. It is also quite matured actually, but number of companies here are very low. Well, see, only I could find only IonQ is actually working on Traptown technologies. Its strengths are high qubit fidelity and long coherence times. See, it actually takes noise head on. So you say that we are there. We are already solving the basic problem. Then excellent control and manipulation of individual qubits. Okay, so basically what happens is trapped ions are well, let's not get into the physics today. Okay, so and naturally fully connected qubits. So all the time the technology is such that it has a lot of strengths, but I'm not sure why not many companies are there. So weaknesses: lower gate operation. This is you build a computer with solid tech, but then its microprocessor is slow. So something of that sort. Scaling to large number of qubits is challenging. I don't know why exactly they are saying it. I have to actually dig more about the physics of it so that we understand. And engineering complexity is obviously there, and most probably that is the barrier for other companies to get into this space. Okay, so the third one is neutral atoms. Okay, and and you see there are a bunch of companies on this. Okay, and the new scientist document actually mentioned that this is probably the most promising tech on quantum hardware. Those strengths: high qubit quality and good coherence times, like us, like the Traptown thing as well. Scalability potential through optical tweezers. Don't ask me what optical tweezers is. Obviously, based on laser, they will do something of that sort, so that you just pick and place the qubit somewhere so that it scales up. And flexibility in qubit arrangement, what I understand by now by this statement is basically, once again, your state space is becomes a lot of choices. So you are not bound to some fixed state space to run your calculation. So that may be the statement here. Weakness, gate operations can be complex. Yeah, obviously, if you are not in standard fork state, your calculation would be complexer. And control systems can be intricate. Anything, we haven't really gone through those complex mathematics of other states while doing those calculations. During our project work, most of us have actually explored this. Companies, many companies, almost like equivalent to the superconducting circuit companies, Qvera, Atom Computing, Pascal Computing, and Quantinum. Quantinum is a UK-based company. Qvera US, Atom Computing, and Pascal both are US. Some California, some Boston. Qvera is mostly Boston. Okay, their stocks are actually costly now. So if you are on investment, uh, you can check those things. Talked about neutral atoms. Then next, go to photonic qubits. This is a story I didn't know. Like I probably heard during my courses, I heard about the first two, like the superconducting and trapped ion kind of hard. Photonic I didn't hear until I read this article. So the potential are room temperature operation. See, this is the differentiator. I would say that if this happens, then we are like miles ahead. Natural compatibility with optical communication technologies. We have optical fibers today, so it's easy. I mean, the most of the technologies are all established. Can be less sensitive to some forms of noise. Obviously, it is light. It is not. It generally not doesn't interact with others. So that's the reason it is immune to bunch of noises, electromagnetic noises for sure. Okay. Weaknesses, challenging in creating strong interaction between the photons. Now, this is a strength, this is a weakness also, right? So, because you can't really influence photons straight away with some other EM interference. So that's the reason. And all the devices needs to be nanoscale. So it's small mirrors and all those stuff. So I'll actually talk a bit few more from my notes, which is not here. So this company called Psi Quantum is a company which is in California, but they have uh, they they have expanded in Brisbane heavily. It's in Australia. They've expanded it, and then they have a roadmap. But by 2027, they will have a how many qubits computer? They're saying. Uh, so the document says they are talking about 10,000 qubit computer by 2027. So think of a scenario where the noise is low and we are talking about 10,000 qubit computer, which would be, with quantum advantage taken in consideration, would be a killer, could be a killer combination. And one of the members of this company, Terry Rudolph, is a grandson of Arvin Schwinger, like the scientist in which who has lot of important work in the quantum one age. Okay, now last but not the least, if I don't talk about this, you will ask questions, because this is the announcement which Microsoft has made recently, last month, end of last month, I guess, that they have invented fourth state of matter. Well, people said fourth, we knew about fourth state of matter, which is plasma, for ages. What's new you are talking about? So topological qubits are has a potential for inherent fault tolerance, significantly reducing error correction and robustness against local noise. So what it means actually, topological qubits are are particles, quasi stationary, I mean quasi existence particle, which uh, which comes into existence by some interaction. I mean, high energy interaction for sure. Okay. One other thing that they talk about is a Mozorona state. Okay, and what Satyan Adela in his announcement of his team was talking about is basically they found a Mozorona. Now, the conflict was Nature published their article with a editorial note that the team has not yet reported an evidence of existence of that, but the method through which they are planning to come about it is reproducible, and that can open up a new direction of research. So that's the reason Nature published the article, clearly stating that the team has not reported the actual measurement or actual state that they have observed and they have measured. Okay, so keep that in mind. It is still in early stages of research and development, and significant challenges in creating and manipulating topological qubits, because Mozorona itself, for example, in CERN, the topmost place for all this particle physics research, they have not yet who reported Higgs boson actually has not reported a Mozorana yet. So it is people will obviously ask questions when somebody claims that they have got a Mozorana. So this was my last slide. There is a reference where I have kept for further reading and stuff. And this is the same folder where I earlier shared my our work group work and some reading materials with all of you. I have just created a separate folder called deck, and inside deck this is there. So with this, I will stop talking, and let's open up for questions if there are. Obviously, I don't know all the things. I'll stop sharing my screen now, and let's go for questions.